So far, we have discussed the method of undetermined coefficients, both in determining the solution of homogeneous and even non-homogeneous higher order differential equations with constant coefficients. Now, the method of undetermined coefficient is so restricting in the sense that the g of x on the right side of our non-homogeneous differential equation is only limited to the functions that were given to you in the example. So those functions are the constant, the exponential function, the sine or cosine function, and we have the polynomial function and a combination of this. So the combination would come in the form of addition, or it would come in the form of products of these functions with the sum of others. So those are the g of x only that method of undetermined coefficients can handle. Aside from that class, then I know that everybody will agree that whenever the g of x function on the right side of the non-homogeneous DE consists of a product of functions already, there's a lot of time that is given to the differentiation of such a function because you are to perform a product rule of differentiation. And the method that I'm going to discuss to you this afternoon, this is actually a special type of method of undetermined coefficient because it will reduce the time of finding the value of the undetermined coefficients for functions that consist of the exponential function and either the sine, cosine, or both having the same argument and a polynomial function. So the name of the method is exponential shift. The rest of the procedures class is actually exactly the same as the method of undetermined coefficients. Now this one, however, was created for the g of x on the right side, which has an exponential function. That way we can save time in determining the values of the undetermined coefficient. So to illustrate what I mean with specific examples, let's start with this first example here. You're given a second order DE, and the g of x here constitutes a product of a third degree polynomial because you have x cubed here and an exponential function. Now, if you are going to use the method of undetermined coefficients, this will be the form of the particular solution as discussed to you last week. Okay, we copy the exponential function and we write the form of the particular solution for this third degree polynomial. So this would be it. And this is what I meant a while ago when I say that differentiation takes a lot of time because you're going to use here differentiation of a product of two functions. And the result would be a left side in your DE, which is very long because if this is to be processed using product rule, you will have two terms here for its first derivative. And for its second derivative, you have already four terms. And those are to be substituted here. So that also entails a lot of time. Now, though this method, if not discussed, you can still determine the value of the A, B, C, D in here using the method of undetermined coefficients. This is discussed. That way, you have an option and you will be able to use it, just use it if there's a need for it to be used, if you want to save time. Okay, if the problem does not require you to use this particular method specifically, then you can use any method that you like to use. But if the problem specifies that this should be used, then this should be the method that you will use. So number one, your g of x should have an exponential function. So it's restricting. If the g of x on the right side of your non-homogeneous higher order differential equation does not have an exponential function, then you forget about this method because this is only in such cases wherein we have an exponential function in our g of x. So this is how we write the form of our particular solution, but this is not how we're going to process this DE this afternoon. We're going to use exponential shift. And from the term exponential shift, we're going to transfer the location of this exponential function here on the right to the left. So we will divide our DE here by e raised to 3x. In that process, your DE now will be written in this way. So you have e raised to minus 3x. From the denominator, we place it on the numerator. And what is left on the right side is just 16x cubed. Now, as discussed as well, we can write the derivatives of our unknown function in the form of a differential operator, the capital letter D. So we do that in here. We change the second derivative and the first derivative to D, and we just copy the constant. And what we do, this e raised to minus 3x, we multiply it with our unknown function y. Because originally, class, if this is to be written in the form of the differential operator, this should be d squared minus 2d plus 5 times y only. So y meaning this is the second derivative of y minus twice the first derivative of y plus 5y. So that's it. But in this case, we now, not the term combine, but you will now multiply this unknown function y in here by e raised to minus 3x and view the left side of this DE as if this one is your new unknown function. If you're going to look at these two, they're just the same. But now in this case, we're going to look at the product of this exponential function coming from the right side, from your g of x and y as your new unknown function. Do you see two functions? You will look at them as if they're just one. Okay? Now, excuse class ha. I'm not sure where is that sound coming from. Sorry about that. Now, so we're going to go to the next page wherein I'm going to show to you the formula of determining the solution of this given DE using the exponential shift. So I'm going to compare this original DE of yours, wherein I've transferred the exponential function to the left to this particular form. So this is our formula. You have in this formula e raised to ax times the function of d times y, and it is to be interpreted in this form. The function of d expression should be shifted by subtracting from the d the a. Where is the a coming from? It's coming from this exponent of the e. And then you have this new unknown function comprising of the product of your y, your original unknown function, and this exponential function e raised to ax. If we're going to apply this principle in here, in this particular equation that we have here, so we can use exponential shift, then what will happen is all the d's that you see here would be now d minus 3. Okay, your a is minus 3. So that is why you're seeing here a plus 3. So that would be d plus 3 here again, and you have here a 5. And we copy this one, the e raised to axy. Based on the formula, this original expression has to be converted to this, since these two are just equal. So now we have e raised to minus axy. This e raised to minus 3x was just transferred here. And you still have 16x cubed on the right side. Just like algebra, you're going to simplify this. So d squared plus 6d plus 9 minus 2d minus 6 plus 5. And we copy this and we copy this. Then again, simplify further. You have d squared, you have 4d, and you have 8. 9 minus 6 plus 5, 8. And we have this. Your original DE, the given DE, was now transformed in this form using exponential shift. So you can only use again exponential shift when the right side of your DE has an exponential function. So with this now, you can write the form of the particular solution of your new unknown function based only on the third degree polynomial you see here on the right side. So your yp, or your e raised to minus 3xy sub p, will not anymore be a form of product of an exponential function and a third degree polynomial, because we already transferred the exponential function here on the left side. What I mean is this. So the form of your particular solution for this new unknown function is this one now. Now, since in your transform DE, you have the second derivative and you have the first derivative, you are to differentiate both sides of this equation. So whatever variable is present on it. So the derivative of your new unknown function is equal to, you differentiate this. Of course, you know how to differentiate, so this will be your answer. Differentiating again, this will be the answer. Now, what will you do with the second derivative, the first derivative, and this form of the particular solution of the new unknown function? You go back here in your transform DE and substitute it, not on the original given DE, but you will substitute on the transformed differential equation. So take note, here you have a 4D and an 8. So that would be done in here when we substitute these derivatives here. Okay, kindly mute yourselves there. So if we substitute on this transform DE, this will be the second derivative. This is 4 times the first derivative. This is 8 times the form of the particular solution of this new unknown function. And we equate it to 16x cubed. The rest of the procedure is exactly the same with the method of undetermined coefficients. You equate coefficients of terms for x cubed, x squared, x, and for the constant. So if you equate coefficients for x cubed, you have your 8a, and in here you have 16. You can solve right away a, which is being equal to 2. If you equate coefficients for x squared, you have 12a here and another 8b here. We don't have any on the right side, so it's 0. Now then we can substitute the a that we have learned here on the first equating of coefficients. That way we can solve for b. So b is -3. For the x, terms having the x, so you have 6a plus 8b plus 8c. Still no x on the right, so it's 0. Substitute again the values you know for a and b and solve for c. Now for d, you're after the constants. So x raised to 0 is 1. So we're referring to the constant. So you have 2b, 4c, and 8d. 2b, 4c, and 8d. No constant here. So we have it equated to 0. If we substitute the value of b and c, d is 0, comes out to be 0. Now, we will substitute the 4 a, b, c, d coefficients in the form of the particular solution of your new unknown function. In here, you will substitute it in here. So this is now how it's going to be written. Now, since this exponential function is first and foremost not written there together with the y, you shift it back here to the right side. So you divide this entire equation by e raised to minus 3x, and it will give you e raised to 3x. And if you factor out x in all these terms, since it's common, then you have x e raised to 3x, then the remaining multiplier to complete this right side. So 2x squared minus 3x plus 3 halves. This is your particular solution. Since this is a modified method of undetermined coefficient, you still need to determine the complementary solution. So you need to write down the characteristic equation. Where is the characteristic equation? It's based on the left side of the given DE, the original one, not on the transformed DE. So you are going to get the roots of the characteristic equation based on this left side of the given DE, the original DE that is. So it's actually in the form of M as discussed, first discussed under method of undetermined coefficients for homogeneous higher order DE. And if you're going to apply quadratic equation, your roots come as a pair of complex conjugate roots. Complex because it has the real and imaginary part. Conjugate since the imaginary parts are the negative of each other. So you learn also that whenever you have a complex root, your complementary solution, we need to account for the real part, and it's being accounted for by this exponential function. So since it's 1, so you only have x here. And for the imaginary part, it's accounted by the pair of the sine and cosine function. So since this is 2i, so you have cosine 2x and sine of 2x. Now, your solution, your complete solution will constitute of the sum of the two. The complementary solution coming from the characteristic equation based on the left side of the original given dE plus the particular solution based on the method of exponential shift. That is, you base this one on the transformed differential equation using the formula, this formula for exponential shift. So this way you get to find the solution faster. Your procedure here is shorter and it's less prone to error compared to if you do not know this and you stick to the original set of procedures for method of undetermined coefficients. Okay, so though if it's not really specified in the problem, you may stick to the what you already know before. But if it's required in the problem that you will apply exponential shift, then you have no choice. You really have to reflect your understanding of this particular method, which is actually just a, shall I say, a modification or a special type of the method of undetermined coefficients, because everything, all the procedures are exactly the same as the method of undetermined coefficients in determining the values of the undetermined coefficients in the particular solution. The only difference is in transforming the original given dE into a form where you already use the equation, the formula for exponential shift. Any question here? So in here, in your example, you have an exponential function and a third degree polynomial. Now, what if you have an exponential function and a sine function? Let's say we have the second example. So actually, the procedure is still the same. We transfer the exponential function here. So that could be done by dividing the original dE by e raised to minus 2x. So it becomes positive here already, leaving only sine x on the right side. If we don't use exponential shift, this is the form of the particular solution using the method of undetermined coefficients. You will use product rule of differentiation. That way you can correctly substitute it here on your given dE. Now, if you're going to change the derivatives here into the differential operator, it would be as simple as changing the y double prime and y prime to d. So d squared and d. You have exactly the same as what we have here. If you're going to apply now exponential shift to this one, all the d's here should be shifted by subtracting from it the a, or the exponent of this exponential function. So since it's positive 2, this is now d minus 2 squared for this one. Minus 2d minus 2 for this. You still have 5 in here. Now your y will not be just y, but now it will have the e raised to 2x. This is now your new unknown function. And again, you simplify this f of d expression, or the function of the expression, using algebra. So d squared, middle term here will be minus 4d minus 2d, so that would be minus 6d. Constant here is plus 4, another plus 4 here, 8 plus 5, 13. This is now your transformed dE. Now we will solve the value of the undetermined coefficients based on the form of the particular solution of the what? Of the remaining function here. And with this new unknown function. So it should be an a sine x plus b cos sine x, because you have a sine x here. Then get the derivatives. So just like what we did with the first example. So get the derivatives of that, and then do second differentiation. This would be it. And then apply the, or rather substitute these derivatives in this unknown function to, take note, on the transform DE, not on the original. So you have here a 6 and a 13. So meaning this will be multiplied by 6, this will be multiplied by 13. This one is as is. So you copy, this one is multiplied by -6, and this one is multiplied by 13. You equate it to the sine function here. Then you equate coefficients. So sine x will have on the left side -a plus 6b plus 13a. And it should have 1 on the right. So if we will simplify, you have -1 and 13. That would be 12a and 6b equal to 1. Since we have two unknowns, we can solve for now the a and b. Then we equate coefficients for cosine. So cosine, -b, -6a plus 13b. -b minus 6a plus 13b equal to 0. We don't have a cosine here. So we get here a relationship between a and b. So you'll have here 12b positive, this -6a we can transfer on the other side, making it positive. So a is equal to 2b. Now, this 2b for a, we substitute in here. So 12a plus 6b. 12a, which is 2b plus 6b is equal to 1. So you have 24 plus 6, that would be 30, and b is 1 over 30. Substitute it in here, a is 2 over 30, or that's 1 over 15. And you just substitute a and b in this form of your particular solution. And it's something like this. Just like what we did in the first example, return the exponential function, shift it back to where it came from. So you place it here by division. So you have now e raised to -2x. If I will use 1 over 30 for these two, then this should be 2 over 30. That will still be 1 over 15. That way, our particular solution is simplified already. So you have 2 sine x over 30 is 1 over 15 sine x. And you have cosine x here multiplied to 1 over 30. Your yc is still the same as the first one because I made use of the left side of the first example. That way, we will not keep on determining the roots of our characteristic equation. So I'm using the same left side. So then your yc will be similar to that in example 1. Your solution will still constitute the sum of the two. Okay, so it's solved faster with less probability of committing an error because we didn't do any product rule of differentiation. Any question with exponential shift? So far, these are the functions that exponential shift can handle. Product of an exponential function with sine, this can also be changed to a cosine, or both the sine and cosine as long as they have the same theta or argument. And product of an exponential function with a polynomial, our first example. So it's restricting though, but this is an alternative process of finding the solution of a non-homogeneous differential equation where the right side has an exponential function and has only the functions mentioned. Do you have any question here? It's okay. Any question? It's okay, Ian. Now, if there are no questions here, we go to a method that you won't really like. I'm sure you won't like it because it will now require you to integrate. But this is another option that you can use for non-homogeneous higher order differential equations with constant coefficient. Okay, with constant coefficient, take note. So meaning if the coefficient of the derivatives of your unknown function or function in your DE is not a constant but a function of your independent variable, this method will not be applicable anymore. Okay? Hindi siya pwede. And aside from that, your characteristic equation, the equation in which we determine the constants, or rather the roots, so that we will know the complementary solution in the method of undetermined coefficients, your roots there should be real. So if the roots of your characteristic equation is not real, let's say for example, it is imaginary, it has 2i, 4i, or I, or it's complex, more so if it's complex, this method cannot be used because this requires that your characteristic equation should have real roots. So meaning your left side of the DE should be factorable. And it will have real roots only. If not, then you cannot use this one. You stick to method of undetermined coefficients. The advantage of this method over the method of undetermined coefficient is it does not have any limitation, on the other hand, on the g of x. The function that is written on the right side of your non-homogeneous DE is not limited this time. Why? Because it does not limit only to sine, cosine, polynomial, constant. It can have products of this. It can have even tangent, ln, hyperbolic. The only limitation for this operator method, aside from that the characteristic equation should have real roots, is that if the one who's using the method does not fully know how to integrate or is not that good in integrating, especially integration by parts. So if you don't like doing integration by parts, I don't suggest this method to you. Okay? And most of the time, you do integration by parts using this method. But before I give you specific examples here, there are three particular formulas that you will encounter in this operator method. And how this formula is to be interpreted is something that I have written here. Okay, I will just place here equal sign. That way, it's uniform in presentation as the others here. So I will place here na lang f of x so that it would be general. Okay, so you have here f of x, and you have here the integral of f of x. Okay, let me explain this. And as to what is this, how do we come up with this expression, that will be illustrated in the specific example. One formula that you can use here in the operator method is when you see an inverse operator. The reason why it's called inverse operator, it's because it's not D, but it's 1 over D. So the D here is still your differential operator. So I'll write it here. The D here represents the derivative of your unknown function. Okay, let's say if it's y, so it's dy dx. Okay, this is the derivative here. So the 1 over d multiplied to the function of x is to be interpreted as you find the integral of this function of x. Whenever you see the inverse operator, that is to be interpreted as the integral of the function that follows it. That is written after it. Okay, so you need to get the integral of that function, and that already gives you the solution of the DE. The other expression that you could see is this 1 over D minus P, where P is any real number. That is why your roots of the characteristic equation has to be real. So P is a constant, it's a real number, and it's in here written are being subtracted from the D, and it's 1 over D minus P times the function of X. Whenever you see this one in your expression, you need to take note, determine the value of P, and make that as the exponent of this exponential function here. This is really class the formula. So this is to be interpreted excuse me, as e raised to px times the integral of e raised to minus px times the function of x, whatever is this function of x, dx. So if this is 2, this will be e raised to 2x integral of e raised to minus 2x f of x. If this is ln, so you place here ln x dx. Okay? Now, if you have here a positive exponent for the e, the exponential function that is written after the integral will be negative. If this is negative, this will be positive. That's just how simple it is. Okay? I will show you later how is it done. Now, the c actually is just an extension of this. Whenever you see more 1 over d minus a constant, in this case, 1 over d minus p1 times 1 over d minus p2 times your function of x is to be interpreted as it should be now consisting of a product of several integrals. So what happens here, you're going to copy p sub 1 first. So you have here e raised to p sub 1x. Of course, the exponential function that should be written after the integral should be negative. If this 1 over d minus p2 is not here, you will right away write here f of x dx. But since you have the second one, you will again write the same form like this, but this time it's p sub 2x for the e. Then you have another integral, and you will have e raised to negative p sub 2x. So positive to negative. Then wala na may nagsunod, no? So you just multiply it with the function of x. Then you will have two differentials of x here because you have two roots from your characteristic equation. That's what that was written here. So the number of roots tells you how many times you will integrate. The number of times you will integrate. Okay? Now, it would be hard to follow if there's no specific example. So we'll have a specific example. By the way, before I forget, the question, Mies, in terms of the root, does it have to be like 1 over d minus p1? Hindi pwede ma-interchange. The answer is pwede kagid ka-interchange. But in the case of the operator method, whenever you exchange the location of these constants here, that also changes the manner you integrate. You will see later when I give you a particular example. But as to the question, is it okay if I interchange? The answer is yes. You will still be getting the same answer. But as to whether it's simple, whether it's complicated, it's dependent on the placement of this, how you place the two roots. Now, I'll go to a specific example. Never mind this first. Let's say you're given this y double prime minus y equal to e raised to minus x. Upon seeing this, I know you will say, Miss Ali, we will just do method of undetermined coefficients because that's very simple. I agree with you. This is very simple. I'm just using this to illustrate to you how the operator method is less prone to error and how it gets the answer faster. The question lang is if you do not know how to integrate by parts compared to the method of undetermined coefficients, which is really very long and lengthy. So this second derivative could be written as d squared, right? And this is not derivative. This is your unknown function. So you just place here -1. And you have here y. Because this y is supposed to be multiplied to this to come up with this. Okay? Then you have your exponential function. This can be factored. If this cannot be factored, forget about the operator method. So it could be factored. So the factors are d plus 1 and d minus 1. Okay, y. Now look, I'm going to transfer this to here. So what will I do? I'll divide. So this is the reason why you are seeing here a 1 over d minus 1 times 1 over d plus 1 times e raised to minus x. Notice as well, nga gin-interchange ko na sila. Ginuna ko sila si d minus 1 and then I followed it with the d plus 1. You will see later why I did that. So this is your exponential function here. Now, the formula which we will use in determining the solution of this DE is letter C, this one. Why? Because we have the two roots here. So I pointed that this one is for the y, this one is for the first 1 over d minus p1, where p1 is 1. And this is for the 1 over d minus p2, where p sub 2 is -1, because this is plus. and this is your function of x. How is it to be interpreted? So isn't it that you're going to get the value of the p sub 1 and make it the exponent of the exponential function here? Then integral sign, since this is positive, this becomes negative. What's the second p? The second p is negative 1. So then you will have here e raised to negative x. Not x because this time your p sub 2 is negative 1. Integral of, since this is negative, this would be positive. Now, so this is your e raised to x. Where is this coming from? This is your function of x based on the formula. So this is your e raised to p1 integral of e raised to negative p1 times e raised to p2 integral of e raised to negative p2 times the function of x dx dx. That's this formula here applied to this particular dE. Now, you can see this red thing that I've written here. You can multiply, or rather it's not can. You should multiply before you do any integration. Since this dot is to be interpreted as a product, then multiply this. Then that would be equivalent to e raised to minus 2x. Multiplying these two gives you e raised to 0, which is 1. So isn't this easy to integrate? If it's 1, you're just going to integrate dx, and that should only give you an x. Now, what will happen if I stick to the original way that I have written it in here? I start with a d plus 1 and a d minus 1 here. Hindi mag-erase to 0. I will have an exponential function here to be combined with another exponential function. You try that at home, that way you will see. So your first integration will not be the integral of a dx, but another exponential function. So the placement of these two really matters as to how easy will your integration be. So as to question, when do we use it, miss? When do we use the easy way? Or what tells us that it's the easy way, and what tells us that it is the hard way? Experience tells you that. You try first doing it, first placement. If you think that that would be difficult to integrate, interchange. Maybe the second one would be easier. But as to what particular thing tells you that you will have an easy integral, sometimes it takes only inspection to know that the argument of your exponential function resulting from the placement of your 1 over d minus p's will simply arrive at an e raised to 0, especially if your function that is given is also exponential. Okay, so amo na ni siya class ha. So if you're going to integrate it, this would be it. So this one was changed to e raised to minus 2x, and I have here dx. So what do you do from your calculus? You integrate this one, the farthest. So this is x. And since you're dealing with an indefinite integral, you should have an arbitrary constant of integration. And that's your c sub 1. This is your answer for your first integral. It should be multiplied to this e raised to minus 2x before you do the next integration. So if you multiply or distribute this to this two, this will be your expression. Right? Amo ni siya, i-distribute mo. Tiini siya karon, ma-by parts ka na dire. Because this is x e raised to minus 2x. I'm sure you know how to do by parts. It was taught to you. So your u is x, your du is dx, your dv is e raised to minus 2x dx. Your v is negative 1/2 e raised to minus 2x. The answer for the first term when integrated constitutes these two. You have uv minus the integral of v du. Minus, this is minus, so that makes it plus. However, the integral of this is another negative 1/2 e raised to 2x. So this makes it negative 1/4 e raised to 2x. So this first term has these two answers upon evaluating the integral. The second term actually will yield negative 1/2 c sub 1 e raised to minus 2x, because the integral of this is negative 1/2 e raised to negative 2x. But since c sub 1 is a constant but unspecified, and negative 1/2 is another constant, you can combine them into another arbitrary constant. And that would be, in this case, I represented it as A. Your negative 1/2 C sub 1 are represented as A, another arbitrary constant. So you have here e raised to minus 2x. And since this one, when integrated, is another indefinite integral, you will have another arbitrary constant. So since I used A here, I used B in here. Okay? Now, the last part is just distributing this e raised to x to all your terms here. So you have 4 terms, you distribute this e raised to x. So what you will have now is this class. After distribution, so a e raised to minus 2x times e raised to x would be a e raised to minus x. Your b becomes b e raised to x. This negative 1/2 x e raised to negative 2x becomes e raised to negative x. And you have here negative 1/4 e raised to minus 2x times e raised to x is negative 1/4 e raised to negative x. If you notice, I have underlined the two in red. Why do you think have I underlined them? These two, the first and the last term. Why do you think have I underlined them? Pareho sila form, no? Naglain lang. Ini arbitrary constant, ini specified constant. You can combine the two because in terms of form, they're just the same. So you may not write this one. Actually, you should not write this one because it's already accounted for in here. So if you factor out e raised to minus x here, actually you will have a minus 1/4, right? An unspecified constant minus 1/4 is still another unspecified constant. So you better write it still as A. Or you may use another letter if you want to, but it's still another arbitrary constant. So your DE now has this solution using the operator method. So you see, it's difficult, Miss, because we need to integrate. I agree with you, it's really difficult because some does not really fully understand how to integrate. Doesn't even master the integration. But this is the operator method. It's an option that you can use. And one particular advantage of this method over the method of undetermined coefficient is this. If you're going to use the method of undetermined coefficients purely in this DE, the form of the particular solution based on the g of x here is a e raised to minus x, right? And based on the roots of your characteristic equation, your complementary equation would be c sub 1 e raised to x plus c sub 2 e raised to minus x. Based on the two roots here, negative 1 and positive 1. Now, if you use the method of undetermined coefficient and you forgot to compare your particular solution to any of the terms that appear in your complementary solution, you forgot that these two are similar in form. So if you process your particular solution in terms of its derivative several times, you process it, you may wonder why is it that I cannot find the A? It's because you failed to modify it. So you should modify your original form to this form. You know this already. And this is the one that you're going to differentiate. And look at it. It's again a product of x and e raised to minus x. So you will have one tedious process of differentiation because you're going to use product rule of differentiation. So that's one advantage of the operator method because you don't have to determine yc and yp. Your process in itself takes care of that. Why? Because this A and B are comparable to your C sub 1 and C sub 2. That should appear in your complementary solution. But we only have one line of solution here based on the integral that we processed. Okay, this is our operator method. Now, any question in this particular part? Any question? Okay, I'll give you another one which will illustrate the use of the first two formulas, this one. this one, the inverse operator, and just one of this. I give you this example. This one can also be solved using method of undetermined coefficients. Okay, second derivative, first derivative, and one here as your function of x. This is your g of x. If we will write this in the form of the differential operator, it's d squared minus d times y equal to 1. Since you have these, you can factor out the d. So you have d times d minus 1 times y, right? And you can place it here. So you have 1 over d and 1 over d minus 1 times 1. You get it? Now, how do we determine the solution of this particular differential equation? So let me just erase this one first, so you will understand. Based on the formula that we have, for the inverse operator, this is the inverse operator, no? It will simply require that you integrate the function, right? If you see a 1 over d, you will just integrate the function. In this case, we'll apply it here. This 1 over d tells you that you will integrate the function. What is your function? Amo ni siya. Ang inyong function subong ini siya. So, and what is this? Isn't this letter b again? So, letter b, what is letter b? You have 1 over d minus p f of x. So, amo ni siya times the function. So, ano siya ang function? So, I write here, your p here, your p is here 1. I use the black ink. So, you have e raised to x, e raised to minus x. And what is your function of x? This is your function of x. We will multiply it by 1. So whenever you have a combination of this, you can even add another one here. You just process it like this. So this should have been integral of the function of x. It just so happened that your function of x class, in the case of the first 1 over d, is this. This is your function of x. So what is the answer for this function of x? The answer for that function of x is this. Another formula. Okay? So that's it. Question. Miss, pwede unahon ni siya ang 1 over d. Dason ini ang 1 over d minus 1. Correct. Pwede gid. Una ka na-integrate. Dason butangan mo sini. Pwede gid siya. Unahon mo bilang ang 1 over d minus 1 here times 1 over d. Then you just integrate 1. Whatever is the answer to that integral, which is x, you process it together with this. Now, you see the reason why I wrote the 1 over d last? Because if you write it, or I wrote it first, because if you write it here last in this particular line, you will do integration by parts. Do it at home and you will see. So kung ginuna ko ang 1 over d minus 1 times 1 over d here, do hapos ang first ko nga integration because that would simply be the integral of 1, which is x. That particular answer will be multiplied to this. So I will have integration by part in here. So that is why I place it last. Whenever I see this one, I also place it last. Especially if I have this. That way, I will not have to do integration by parts. Okay, so if we process this, yung muning una yung integral plus e, so negative na siyang answer. Negative e raised to minus x plus c sub 1. That's your first integral. Then you multiply first. That would be negative 1, and you have c sub 1 e raised to x. Then integrate. You have negative x plus c sub 1 e raised to x plus c sub 2. Your second arbitrary constant. This is already the solution of your DE. Now, notice that your particular solution part is negative x. Look here. You have a constant here. Right? It's a constant. If you wrote this using the method of undetermined coefficients again, you would have written yp is equal to a. Here, your roots are 0 and 1. So you will write yc is equal to c sub 1 e raised to x for this one and c sub 2. I'll say here plus. Okay, this one is for the e raised to 0, and this one is for, of course, the e raised to x. Again, look, they are the same. With the method of undetermined coefficient, there is a need for you to modify this. You should have written it as a times x. And this is the one that you will differentiate. If you forgot that again, then everything will be wrong, because we are required in using the undetermined coefficient to always compare our complementary solution to our particular solution form. Should there be any terms in our complementary solution that is similar to that in the particular solution, it is the particular solution that we modify. If we miss that, matingala ka, why is it that I cannot solve for the undetermined coefficient? It's because you haven't modified it. So while in here, in this method, there's nothing to worry about it because it takes care of that. You don't have to think of YC, of YP. You have only one line of solution, though you need to integrate. Do you get it? We have one remaining topic in non-homogeneous higher order DE, and that's the most versatile. There's no restriction for it. Wala siya restriction, so it does not have restriction on the G of X. It does not have any restriction either on the roots of the characteristic equation.